Okay, we are still on momentum and impulse, and we will be looking at conservation of linear momentum, the and elastic and inelastic collisions. The elastic and inelastic collisions, we will look at them in the other lesson. But for this lesson, we are only focusing on conservation of linear momentum. Okay, before we get into the conservation of linear momentum, you need to understand that whenever two or more objects interact with each other, that whole thing is called a system. When a group of two or more objects that interact is called a system. A system is when two or more objects interact with each other. That's a system. We focus on that. That's a system. And okay, let's now look at these two balls colliding. We will have these two balls, ball A and ball B. Where can I get a ruler? Yeah. Okay. Yeah, I think this is fine. Yeah. Yeah. Okay. We have these two balls on a horizontal lane. Now these two balls are interacting with each other. This means we have a system. This is a system of colliding balls or objects. They are both experiencing horizontal forces that will change the momentum of each. They are both experiencing. We dealt with collisions. When we were dealing with collisions, when we were dealing with collisions, I did mention that Newton's third law still plays a huge role here. Newton's third law. Hey, my lines are not perfect. Okay, let me. Okay. Yeah, when we were talking about collisions, I did mention that objects exert forces on each other. Two objects exert forces on each other, and this force is equal. So this side we have F force of B on A. This is force of B on A, force exerted by B on A, and this side we have force exerted by A on B. But now in this case, in this situation, we also have another force. We also have other forces like and this other forces, it's what? This is friction. Friction is represented by a small letter F, and then this is also friction. This is friction experienced by B, and this is friction experienced by A. One friction and the other is the force due to actual collision. Always keep this in mind. During a collision, object A exerts a force on object B, and as I've explained, according to Newton's third law, an object B exerts an equal force on object A in the opposite direction, as I've indicated here. These reactions that I've spoken of, these forces, they are internal forces. These forces that take action during collision, they are internal forces, and internal forces are described as the forces between objects found inside a system. Internal forces, internal forces. So it's a very simple, it's just forces, between objects. It's just forces between objects in a system. It's just forces between objects in a system, and the mass of the system is constant and no net external force acts on the system. There is no other external force that will act on this system. And when the conditions are like that, when the mass is constant and there is no other external forces acting on the system, the entire system is said to be an isolated system. What is an isolated system? An isolated system is a system on which the net force, the net external force, not just the net force, but the net external force acting on the system is zero. The isolated system, isolated system, the F external is equivalent to 0. External force acting on the system is equivalent to 0, and the mass remains constant. If a net external force acts on a system of colliding bodies, the total momentum of the system will change during collision. Something you should pay full attention to. And if we ignore all the external forces, then the total momentum of the system will not change. This means the total momentum of an isolated system will not change during the collision. It means the total momentum will not change. So by default, for us to be able to observe the law of conservation of linear momentum, the system should be isolated. The system should now be isolated. Okay, let's now focus on the law of conservation of momentum. Let's now look at the law of conservation of momentum. Let me erase everything that I've thrown here so we can focus on the law of conservation of momentum. Okay, let's look at this. Law of conservation of linear momentum states that the total linear momentum of an isolated system remains constant or is conserved. The total linear momentum of an isolated system remains constant. What do they mean by remains constant? You should think of this. It remains constant before and after collision or before and after release. If it's a gun, maybe. If it's a situation similar to a gun, it would be before the release of the bullet and after the release of the bullet. If it's cars colliding, it will be before those cars collided and after they have collided. That's why they say it remains constant before and after something that was expected to cause an interference. Yeah, before and after something that was expected to cause an interference occurs. Okay, now let's get into the real things. Let's get into the real things. We know this. We know this. We know that momentum is equivalent to the product of mass and velocity. We know that momentum is equivalent to the product of mass and velocity. So let's look at the momentum of objects before they collide. We will have the momentum before momentum before collision, it's gonna be the momentum of object A plus the momentum of object B. Here we are looking at the momentum of objects before they collide. That's why we consider the momentum of both the objects. And this is just, you just have to distribute these two, which is just gonna be mass of object A by velocity of object A, not velocity, initial velocity of object A, initial velocity of object A plus mass of object B by initial velocity of object, by initial velocity of object B. So when you have something like this, you will also have the momentum after collision. Momentum after collision, it's just momentum of A plus the momentum of B. But in this case is momentum of A after a collision by final velocity of A. This was supposed to be A here. This was supposed to be A, not B. Plus mass of A by final velocity, mass of B by final velocity of B. This is momentum before collision and momentum after collision, or momentum before a form of interference and momentum after that form of attempted interference. Okay, this thing will be the sum of momentum before collision is equivalent to the sum of momentum after collision, and this overall is just equivalent to the mass of A by its initial velocity, by the initial velocity of A, plus the mass of B by the initial velocity of B is equivalent to the mass of A by final velocity of A plus the mass of B by final velocity of B. And this formula here describes this whole is the mathematical expression of this entire definition. Is the mathematical expression of this entire definition. Let's now look at examples. Okay, let's look at the first example. This example, there are conditions in this example. Here, the objects collide and stick together. In this situation, the objects collide and stick together. Okay, let's now read the question. The question reads: a car of mass 800 kilograms traveling at 20 meters per second east, and a truck of mass 1000, a car of mass 800 kilograms and a truck of mass 1500 kilograms traveling traveling at 15 meters per second west on the same road. Ignore the effect of friction. The vehicle collide head on and stick together. Here, they collide head on and stick together during the collision. Calculate the velocity of the car system immediately after truck system immediately after collision. Okay, let me start with an illustration. This is our car, this is our truck truck and a small car. The car is moving east, the truck is moving west. These two collide. Now we have to calculate the velocity of the car truck system immediately after collision. We have to calculate the velocity after they have collided. This is just how the system looks. So now let's calculate it. A possible way for us to calculate velocity is to use this formula. The sum of momentum before is equivalent to the sum of momentum after. Okay, let's now look at this, where we'll have mass of the car by initial velocity of the car plus mass of the truck by initial velocity of the truck is equivalent to mass of the car by final velocity of the car plus mass of the truck by initial velocity of the truck. Okay, now let's substitute and solve this. Before the collision, these things will have a separate mass, but after the collision, these things will stick together. So the mass of the truck and the mass of the car will now just form a new bigger mass. I will call it mass CT, which is mass of car truck system. But their velocities will also now be one final velocity. Here it's supposed to be one final velocity. It will now be one final velocity. We'll also now have a final velocity like this. So let's now substitute this side. Let's substitute the mass for our car. This, before collision they were moving in separate directions, but after collision they stick together and started moving together. Pay attention to that. The car has a mass of 800 kilograms and it's moving at a speed of 20 meters per second east. As I've indicated, east is positive though, so this will remain positive. And the truck will have 1500 and minus 15. So now let's see this one. 800 by 20 is 16,000. We will have 16,000 plus this is gonna be minus 22,500, and this side we will now have to substitute 2,300. This 2,300 by final velocity, I will now say final velocity CT. This 2,300 that I've shown here, is the 800 kilograms for the car plus 1,500 for the truck. So let's go back to our problem. 16,000, not 1,600, 16,000 subtracting 22,500 is minus 6,500 is equivalent to 2,300 final velocity, and my final velocity will be minus 2.83 meters per second. Obviously the direction will be east. Not east, will be west. Obviously the direction will be west, given that I've chosen this as my direction. Let's now go to the next question. This question, it was when the objects collide and stick together during the collision. The next question that we are looking at right now is when objects are exploded apart. Yeah, it's when objects are exploded apart. It's when objects are exploded apart. This is similar to when you release a bullet from a gun. They are exploded apart. Okay, let's look at this. Two trolleys, A and B, are moving to the left. These two trolleys, they are initially moving in the same direction on a frictionless surface at 3 meters per second. Okay, initially they were together. As shown in the diagram below, a trolley A of mass 2.2 kilograms is connected to a trolley B, a trolley B of 1.3 kilograms by means of a compression spring. Ignore the mass of the spring. The compressed spring between the trolleys is released and the trolley B moves to the right at 2 meters. They are released and trolley B moves to the right at 2 meters per second. Calculate the magnitude and direction of the velocity of trolley A after the spring is fully released, after the explosion. Okay. Before, when they start, they only have one mass. Let's start with the formula. Before explosion, after explosion, of which we have here we'll just have mass for total of the trolleys, mass of the trolley system, and its initial velocity is now equivalent to mass of trolley A and the final velocity of A plus mass of B by final velocity of B. The mass of trolley A, the total mass of trolley A, of the total mass of the trolley system is 3.5 kilograms. The direction, they are saying they were moving to the left. Okay, let's take our left. Here we'll have left and here we'll have right. Let's take our left as positive and our right as negative. Let's take our left as positive and our right as positive. So our left as positive and our right as negative. So we will have plus 3 meters per second. This 3 meters per second. Now the mass for trolley A is 2.2 kilograms, and we are missing the final velocity for trolley A, and then the mass for trolley B is 1.3, and the direction, it is moving to the right. The direction will be -2. Okay, and then here I will have 10.5 is equivalent to 2.2 final velocity of A plus into minus 2.6, and then I will now have 2.6 coming this side. I will have 13.1 is equivalent to 2.2, and 13.1 2.2 will therefore be equivalent to 13.1 divided by 2.2 will result in a final velocity of 5.96 meters per second. And because this is a positive answer, it means that it will be to the left. As I've chosen my left direction as positive. Let's go to another situation now. This other situation is when the objects collide and separate. separate. They collide and separate. They collide and separate. They don't collide and stick together. They don't start as sticking together and explode and separate. They start separately, they collide and separate again. Okay, so a 0.3 kilogram volleyball is thrown horizontally at 2 meters per second. A 0.3 volleyball is thrown horizontally at 2 meters per second west. In this case, west negative, east positive. West, it strikes a stationary basketball of mass 6 kilogram. It strikes a stationary. This stationary already gives you the idea about the initial velocity. It means the initial velocity is 0 of this basketball is 0. The volleyball rebounds east at 0. The volleyball rebounds east at 0.8 meters per second. What is the velocity of the basketball after the collision? There are two separate objects before the collision. This is a hint. Before the collision and two separate after the collision and two separate after the collision. Okay, let's now look at our solution. Obviously we will start again with the formula. We'll have before collision and after collision, which is just mass of the volleyball by initial velocity of the volleyball plus mass of the basketball by initial velocity of the basketball is equivalent to mass of the volleyball by the final velocity of the volleyball plus mass of the basketball multiplied by the final velocity of the basketball. And when we substitute now, the mass for our volleyball is 0.3 kilograms. Our velocity there, it was 2 minus 2 because it's moving towards west. It's moving towards west. The volleyball, it's minus 2 because it's moving towards west. Then plus mass, what's this? The mass of the basketball, which is 0.6 kilograms. The initial velocity is 0, and here the mass is still 0.3. The final velocity now is 0.8 because it's moving towards the east. And now here the mass is still 0.6, and we are looking for the final velocity of the basketball. So this will give me a minus 0.6 plus 0 will be equivalent to 0.24 will be equivalent to 0.24 plus 0.06, not 0.06, 0.6 final velocity of beam. And now when I transpose this thing, this side, I will have minus 0.84 will be equivalent to 0.6 final velocity, which is therefore equivalent to final velocity is equivalent to minus 1.4 meters per second. Because it's negative, it's west. And this concludes our lesson.